thinking about what topics could I cover today, and trying to understand the audience a little bit. I see that we have a lot of international people, so this is really terrific. And this is something that, our remote model now makes it possible. So probably something that will be nice to continue doing in the future. So I entitled this talk as selected topics in radiation detector characterization. And so in the coming hour, I'm hoping to just give you a little bit of flavor of the type of things that you might want to think about, when you do advanced radiation measurements for various applications, especially those in nuclear security and nuclear science. In fact, I have 4 things, basically. I was thinking about how much can I talk about in an hour, and I decided to cover these 4 things today. I'm going to talk about characterization of the light sensors. Then I'll talk about light collection. So you will see a lot of, when it comes to radiation detection, one class of radiation sensors involves production of light and collection of light and seeing very faint flashes of light. So we'd like to talk a little bit about that, how to do that well and how to understand that better. Then I'll talk about calibrations, and not so much about calibrations of smaller detectors, but of very large detectors. So something we have been working on lately are very large detectors that can be used for monitoring nuclear reactors from large distances using anti-neutrino signal. So that requires really large detectors. These detectors need to be calibrated so that we can understand well how efficient they are, and how well they perform, and are they actually seeing the signal, or are they seeing something else? So, so I'll try to cover a little bit of that, so you get some picture of how this is done. And then finally, I'll talk a little bit about how important modeling is for understanding detector operation. So we need to understand the physics of detector. We can describe it through the model. We can simulate what detector should see. And if we truly understand it, if we are able to describe it well, then once we characterize detector, the signals that we see on the detector should somewhat resemble, what we used as a model for that detector, right? And how we simulated it. So I'd like to give you some examples of that and how that's done. So in fact, and because these are 4 sort of separate topics, I like to start really just spend I'll try to stay within about 15 minutes for each topic, and then, or maybe 10 minutes, and then stop and see if I can field any questions on that topic before we move to the next one. Okay. So let's start with the characterization of the light sensors. So and in fact, I have 2 screens here, so I will be watching your chat messages. Hopefully I will not miss anything. And I will be writing on my iPad, so this is why I'm looking down. Okay, so start with the scintillation detectors. So how do scintillation detectors work? You can see a prepared scintillation detector here, which is basically a research type detector that some of my students put together. So a couple of things that you will notice here. So there are a couple of elements of the detector. In fact, there are 2 major elements. So there is, let's see my color here. Okay. You will see this bottom part here. This is actually a scintillator. This is a piece of material which will produce flashes of light, weak flashes of light when the radiation is incident on it. And it's wrapped in with black tape. As you can see, we want to keep it light tight. The reason we want to really keep it light tight is because these light flashes are very weak in comparison to all the light that you will see around us, right? So even what we think of total darkness is still very bright, in comparison to the flashes of light that we are trying to see. So, so we need to wrap it, keep it very dark, and then we observe it with a very sensitive light detector. And this is what you see on the top here. I'm trying to change the color. So everything that you see up here, it's a very large photodetector, very sensitive photodetector, which is called a photomultiplier tube, or PMT. Okay. So the way this works, right, is we produce flashes of light, these flashes of light, then radiation interacts with the scintillator, produces flashes of light, and this light, sort of, you can think of it as bouncing all over this scintillator. It enters into the photomultiplier tube, and ultimately we get some kind of signal here at the output, which is electronic signal. Okay. So there has to be some conversion that will take place inside of the photomultiplier tube, how we are going to convert the light into the electronic signal. Okay. So the way that happens, so the best way to explain that is to look at the structure of the photomultiplier tube. And what you see on the right side here is a photograph of one of these very sensitive photomultiplier tubes that is actually used in some of the physics experiments. So there are a couple of things you see here. There's this outer glass here, and then you see the sensitive element, which is inside here, which will be used to convert the light into electrons. So we need to convert light into electronic signal, and the first step in doing that is what's shown on the right here. Is we have light incident onto this element of the detector, which is called the photocathode. So what happens is that light photons get converted into electrons with some efficiency. So what's shown here is that every single photon gets converted into one electron, and then this electron travels down here. And this is not quite right, because it would be very nice if we could convert every electron, every photon to electron, but in reality, we have some efficiency with which that is achieved, which is less than 100%. But what happens now is that we have the single electrons physically being accelerated with the electric field down to a series of electrodes, which are called dinodes. And as these electrons propagate through the structure, they get multiplied. They undergo sort of avalanche multiplication. And the reason this happens is simply because we apply strong electric field. We accelerate these electrons such that when they're incident onto each subsequent electrode, they release additional electrons. Right? So it's a process of multiplication. As we go through the structure, essentially we multiply this signal by a very large amount, by factors of million, 10 million, even greater numbers. So depending on the number of stages that we have here. So whereas we start with maybe only a few electrons on one side, we end up with very large electrical signal on the other side that we can now detect relatively easily. So this is how this works. And as I said, we would like to convert every photon into electron, but we can do that only with finite efficiency. The efficiency with which this is done, it's called quantum efficiency. You can think of this number, which is here on the ordinate of this plot. What this number means is the ratio of the number of electrons that you produce for the number of incident photons. And this efficiency is a function of the color of the light, which is incident on the photocathode. So different color of light means different energy of the photon, and different energies of the photons have different probabilities of releasing those electrons from the photocathode. Yeah. So depending on the type of the photocathode, and there are many different curves that you see on this plot here, you can get different efficiencies, but you can see they can be typically in the neighborhood of, somewhere like 20% or so. So which means maybe only 1 out of 5 of these incident photons may be converted into electron, and we have lost the other ones, right? So we'd like to increase the efficiencies. Sometimes, it's possible to use photocathode materials, which have much higher efficiencies, but these are typical numbers that you get. And then this is not everything, right? So let's think about what we are trying to detect. We are trying to detect emission from the scintillator, and the emission from the scintillator has some spectrum, right? So there is some range of colors that scintillators produce, and an example of that is shown here on the right. So you can think about, you try to overlap one of these curves, which represents the range of colors that are emitted from the simulator with the probability of its conversion into electron, which is shown on the left, right? So it's a product of these two curves that you want to maximize, which will maximize the number of electrons that you can get and multiply, right? So this will be the signal that you're trying to see. So how can I measure this quantum efficiency of a photomultiplier tube? There are a couple of ways to think about this, and I like to think about this as, at least there are two pieces of this problem, right? So, one piece of the problem is how do I count the number of electrons, right? I need to count the electrons on one side, right? Which is, how many electrons I have produced. And then I need to count the number of photons that are incident. So I'd like to take a ratio, right? My quantum efficiency will be a ratio of the number of electrons that I measure and the number of photons that are incident. And I'll talk a little bit about how I count electrons momentarily. But with regards to counting photons, so in an experiment, how I would do that, perhaps, is by using some kind of calibrated source of light where I can actually count photons. And maybe one way to do that is I could use, for example, a laser for which I can measure the energy of the pulse, right? So let's say that I have my photomultiplier tube. Here I'm trying to characterize, and I have some kind of laser, right? And lasers have, very nice collimated, produce very nice collimated beams. So I can try to measure the energy of that beam. So I would make, I would put some kind of energy meter that I could use here. And I would produce a pulse of light here out of this laser, and I would measure its energy. And this is easier said than done because we are trying to see a very small number of photons, right? So each photon, energy of single photon will be very small, right? So energy of a single photon is a product of the Planck constant and the frequency of the photon. And if you look at the energy of a single photon, for example, from the scintillator, which is in the region maybe of about 500 nanometers, you'll find that the energy of that electron will be approximately 2 electron volts. And this is only on the order of 10 to the minus 19 joules, so extremely difficult to measure. Okay? So one way how I can remedy that is to produce much higher energy by the laser, but then filter it by the known amount. Right? So I could introduce maybe some filters that I can put in here. If I know exactly what those filters are, you can imagine that I could now attenuate this laser by the known amount, such that I get just the requisite number of photons, which is not a very large number of photons incident onto these photomultiplier tubes. So that would be one trick how I could use to count the number of photons incident onto the photomultiplier tube. Okay, and so now let's look at this part, which is counting electrons. How do I do that? And I said that the photomultiplier tubes are incredibly sensitive devices, so they can measure individual photoelectrons, right? And individual photons. If you convert individual photon into photoelectron, you can see that single electron. And this is an example of an experimental measurement of something that is called the single photoelectron spectrum of such a device, right? So what's on the horizontal axis is essentially the amount of signal that I get at the output of the photomultiplier tube. And on the vertical axis is basically how frequently, it's a histogram. So here on the vertical axis, I say how frequently I get that outcome. How frequently do I get this type of signal, that type of signal, etc. So when I measure basically output of photomultiplier tubes with a very weak source, let's say that I have a single or maybe 2 electrons or 3 electrons, 3 photons incident onto a photomultiplier tube, I will produce a very weak signal, but I can measure it, right? And this is what I see here. So then I histogram all these outcomes, and I get this curve, which is shown here in the blue, and it has this characteristic shape. So now this is an example really of how I can use, something I know about how the photomultiplier tube should work in order to try to reconstruct what this photomultiplier actually sees, right? So in this example, you can see these red curves, right? And this is basically a fit to this experimental data. I can construct several of these red curves and I can try to sum them, right? I sum them together such that I can reproduce this experimental data, right? So what are they? I can see this first bump here, and this first bump represents detection of a single electron in my photomultiplier tube. Then exactly twice the distance, I guess, from the zero here, I have a detection of two signals, two electrons at the same time. So this would be a double photoelectron signal. Then I have detection of three, etc. So I can fit my experimental data basically to a series of outcomes, right, where I can see one electron at a time, two electrons at a time, three electrons at a time, etc. Right? So now imagine when you know that, right? So now you decided that this here represents one photoelectron. So if I see this voltage, this integral here will represent some kind of voltage that I measure at the output of my photomultiplier tube. If I detect a voltage which is 100 times this number over here, okay, then this will represent 100 photoelectrons. And this is how I will be counting electrons that my photomultiplier produces, right? So going back to this image, now I can send a known number of photons onto the photomultiplier tube. I have characterized what a single photoelectron looks like, a signal from a single photoelectron looks like. Now I can count the number of the photoelectrons based on the strength, on the magnitude of the signal that I get from the photomultiplier tube, where the unit of my signal will be this single photoelectron, right? This is my unit response, right? So this is one way how I would really have a really good handle of each quantum of information that I get in my system, right? I'm measuring very discrete quantum information. The number of photoelectrons that I measure represent everything that I know about the radiation interaction in this detector. I know how many of those photoelectrons I produce in my photodetector and when they arrive. Basically, that's the extent of my knowledge of what's happening. So, so with that, I'll take it to the next level. I say, well, let's look at a really big experiment and what kind of problems, could I encounter in a really big experiment. So what is this? This is a Super K experiment. It's a Super Kamiokande experiment in Japan. This is a very large water-based detector, which has a very large number of photomultiplier tubes, right? So all of these little things that you see here on the side are the photomultiplier tubes, huge number, thousands and thousands of these very sensitive photodetectors. You can see technicians or scientists in this raft here, because the detector is only partially filled, they're servicing some of these photodetectors here. And so these kind of experiments are kind of like the other extreme from what you've seen in the beginning, and I'll return to it for a second. This is the type of detector maybe that you would put together in a student laboratory. You would investigate how it performs in various applications that are more sort of tabletop type. But then when you go to the next level and you talk about things like trying to, for example, detect reactors at a distance using antineutrinos, which is one of the really cutting edge problems that you're trying to cutting edge technologies you're trying to develop for nuclear security. Then you have to worry about how you handle systems like this with a very large number of photodetectors with a huge medium that produces light. And problems here are immense. You're trying to see very, very weak flashes over long distances with a very large number of photosensors. And it's very likely each one of these photosensors will maybe see only one photon at a time, because imagine that you have maybe only 100 or 1,000 photons and they will be dispersed among thousands and maybe on the order of 10,000 photodetectors. So one of the really interesting things that you have to worry about that you would not think about maybe is the radioactivity of the photomultiplier itself. Okay, so if you look at the again, let me return to the photo here. The sort of the interface of the photomultiplier tube is glass, right? And glass will contain various radioactive contaminants. Okay, in fact, every material contains various radioactive contaminants. And you have to take really special care to make it cleaner if you wanted to make it cleaner. But normal glass will be quite radioactive, in fact. And so what will happen is that that radioactive decay, what can happen is that radioactive decay in the glass, in fact, can produce gamma rays. These gamma rays can interact either in the glass or they can interact in the neighborhood of the photomultiplier tube. They can produce very weak flashes of light, which look just like these photons that you're trying to detect, you know. So, so one of the important sources of background that you need to reduce is going to be this radioactivity of the photomultiplier itself. And so there are special types of glasses that are being developed in order to do that. This shows one of the recent results or special types of glass that are developed. So what's shown in the black here is the special glass, which is less radioactive than just the regular glass, which has all kinds of contaminants that are radioactive. These measurements are made with a high purity germanium detector. I see that there is a question here. Neutrino flavors and how we can detect all types of neutrinos. Yeah, thank you. Well, okay, so I was not planning to talk about that, but that's a great question. So, yes, the neutrinos are these really, really interesting particles. We still don't know many things about them. And one of the really interesting properties is they oscillate. So as they propagate from the source where they're produced to, sorry about that, as they propagate from their source to detector, wherever place they're being measured, they can oscillate through flavors. So they can be detected in different flavors as a function of their energy and as a function of distance they travel. So there are different methods how they can be detected that depend really on the types of interactions that different flavors undertake. Okay, so for the nuclear security, which I like to concentrate on here, we are mostly interested in electron antineutrinos. It's a one type of neutrino called electron antineutrino. And electron antineutrinos are interesting because they're produced in the beta decays, and we see a lot of beta decays in nuclear reactors. So so what's really happening is that we want to use a reaction that is very sensitive to that particular mode of interaction, but not to another type of interaction. So other types of neutrinos. And that interaction that we typically use is called inverse beta decay, where antineutrinos interact with protons to produce positrons and neutrons, you know, so we try to detect those in coincidence. Sorry, I'm unable to turn off my notifications. You know, I tried everything. Okay, so I hope that that is just a short introduction, but I didn't want to sway, you know, move too far away from the subject that I want to cover, all the subjects that I wanted to cover today. So I will continue with what I was talking about. So this was the radioactivity. And so the next thing I'd like to just cover here is talk a little bit about other types of sensors. And one of them is called the silicon photomultiplier. And the silicon photomultiplier is a type of photodetector which is significantly more modern, okay? And it's still undergoing rapid development. So there's a lot of interesting things that are they're coming out of both research laboratories and the companies. But the difference is that this is a little bit different method of detection in a sense that each one of these photodetectors is composed of a very large number of small cells, in which one of these cells can either detect photon or not detect a photon. So we basically rely on this idea that we take maybe a large number of photons and we disperse them onto this surface, and we basically count on a very low probability of seeing every single any two photons basically land on one of these cells, because each cell can count only one photon at a time. So we essentially just count the number of cells that fire up, and this is the measure of the number of photons that are incident onto this device. And so it's almost like converting analog information directly into digital information. Imagine I have a number of photons incident here, and I get some electronic signal, which is a number, right? The number of photocells that are firing, and that tells me how many photons are incident. So I basically go from, I undergo some kind of analog to digital conversion by doing this. So how does the signal look like? It looks a little bit like this. There's something that is equivalent to that single photoelectron signal that you might call a single cell signal. So you can count basically events in which only one of the cell turns on, or two cells turns on, three cells turn on, four cells, five cells, etc. So this is real, in fact, real experimental data that you see in the experiments. Okay. Okay. All right, and finally, I just want to highlight also one of the really new devices, which is called the large area picosecond photodetector. So this is sort of on the bleeding edge of the technology now, which will possibly enable some really exciting measurements with special types of scintillators that are very fast. And this is a sensor which, as its name says, it's very fast. It's picosecond. It has a very fast produces a very fast signal, so it can measure very fast events. And it's made. It uses a different principle. It's based on something called the microchannel plate. So I just want to show you, how this looks like, how this works. In a microchannel plate, what happens is you can think of having a channel which is electrically biased, such that the incoming photon can be converted into electron. This electron then bounces many times. So there's different paths that are shown here, and it transits through this channel. As it transits through this channel, it's being multiplied, and what you get at the output is basically a very strong electrical signal. And because this is there are many channels, then the position at which a photon is incident can also be converted into a position at which the electron is ultimately produced, right? So there's basically sensitive conversion from the photon to the electron, and at the same time, there's also position sensitivity, because I can determine exactly the location at which the electron is incident. So I can think of actually detecting various positions in this type of device, ultimately. Okay, so that concludes that first topic. So maybe I'll, I spent already half of my time, so to speed up. Are there any additional questions about this? And I'm just scrolling here. I see a lot of participants, but I didn't want to take any questions related to this before I move to the next topic. Could you talk about, Professor Potts is asking, could you talk about SIPM arrays for imaging? Absolutely, right? So let's look at this particular example here. So in this example, you can see what is called an array, right? So each one of these little elements here, so let me try to draw it here. I hope you see that. So each one of these elements you can think of as a single photodetector, right? So each one of these has many small numbers of these photocells that I talked about, on which you can count the number of photons that are incident on them. But now you can think of this as a sort of a pixelated readout. So if my photon, for example, lands over here, right, I can I can detect this position. I can detect that particular. I can detect signal from that particular element of an array, right? And in that way, I can infer something about the optical system that basically sends these photons onto my photodetector. And if I cleverly design that optical system in a way, for example, by using a number of scintillators which are arranged in segments, I can then, through multiple interactions with those segments, I can infer something about, the direction from which radiation comes from. In fact, that was, going to be something that I was going to highlight next. So thank you very much for that question. And that there's a question also about the efficiency of the SIPM array. And it takes one photon at a time. Should there be that time associated with that? Great question. So I will try to clarify what I meant here. Imagine that I now just magnify this one element over here. So I magnify it like this, and I have maybe thousands and thousands of little pixels here in each one of these. Okay. So imagine now that I have maybe 100 photons incident at the same time. Choose a different color. I have maybe 100 photons incident at the same time onto this array. Okay. Each one of these pixels can see only one photon. If I had 2 photons incident at the same time on one pixel, I would still detect the same signal as one photon, right? So that's one of the limitations. By the virtue of the fact that the number of these cells, which are shown in red here, is much larger, than the number of the photons that I have incident onto this array, then the probability of any photon, of any cell seeing more than one photon is actually quite small. Right? So that's the whole idea, right? Why I can count them is simply because the probability of 2 photons or more than one photon landing on a single cell is actually quite small, simply because of the ratio of the number of cells to the number of photons being so large. And that's the trick. That's exactly the trick. So, and then there's a question about the efficiency. So in fact, the photomultiplier tubes, so there are other things. There's the quantum efficiency, and it turns out that the quantum efficiency of these silicon photomultipliers is actually much better than the quantum efficiency of the photomultiplier tubes. So, and the question is, what is the count amplitude decreasing? Why is the count amplitude decreasing as more cells are fired? Yes, I think this was related to this particular question. And this here is actually a spontaneous, this could be one of 2 things. This could be the measurement of a spectrum when you have a very weak source of light incident onto silicon photomultiplier array, or this could be simply spontaneous electrical noise that you can get where these cells will spontaneously fire simply because they're biased strongly. So every once in a while, you will get some thermionic emission, and some of these cells will fire, and they will more frequently fire as singles. So more frequently, you will see 1 cell firing, then sometimes you will see 2 at once, then sometimes you will see 3 at once, sometimes you'll see 4 at once, sometimes 5 at once, etc. The probability of seeing more and more at once is being reduced as the number of cells increases. Yeah, I hope that explains it. And then another question, can I specify dimension of a single cell of a SIPM? So I wish I could answer that question. I like to say that I think it's on the order of maybe 10 microns or so. Maybe Professor Pozzi knows the answer to that. I think it's on the order of 10 microns or so, I think, for every single cell. I need to look up the technical specifications, but it will be on the order of microns, maybe tens of microns. Let me see if I covered everything. I think I did. All right, great discussion. Yeah, thank you for all these questions. This is excellent. All right, so let me move on. I promised to talk a little bit about light collection. All right, so here we go to the segmentation. I promised to talk about that. So yeah, it's a great intro to that. And this is a big topic, and Professor Pozzi works on that, and I work on that also. This is this idea that you can segment the detectors, and you can see that these detectors, this is basically a scintillator, what you see here. There's a couple of rods, In fact, this is segmented in a very special way. So there is the central module, which is finely segmented, and that's what you see over here. And then it's surrounded by a more crudely segmented set of scintillators. And it's instrumented on two sides. And one side is instrumented with the silicon photomultiplier. The central module basically looks at the light from this, silicon photomultiplier looks for the light from the central module, whereas the number of photomultiplier tubes looks for light from these surrounding modules. Okay, so, and then you look at this from two sides, and I'll explain that in a moment. So we can use this for various things, and one of the ways you can use this is to detect neutrons and gamma ray scattering off of these scintillators, and the physics by which these particles scatter and the signals they produce in different segments can then be used to infer something about the incoming direction of radiation. They follow very specific, physical rules, right? So physical laws, and because we know those laws, right? By measuring which of these segments turn on and where the event takes place inside of this kind of assembly, we can reconstruct the direction from which radiation arrives. Okay? So this is the kind of the idea why we like to make this kind of more complex radiation detectors. Now, I'm particularly interested in if you can use this type of detector to make better measurements of antineutrinos. And the idea here is that, especially in the central module, in the detection of antineutrinos, inverse beta decay process, what happens is that a neutron, which is basically produced, carries some of the momentum of the incoming antineutrino. And if we capture that neutron at some distance away from the direction where the other particle is produced, which is positron, then we can learn maybe something about the direction from which antineutrino has come, right? And the reason we can do that is because we have this pixelation, so we know where events take place, with the resolution of these scintillators, and we read them out with these pixelated photodetectors. So that's the idea. Now, to do this well, you need to collect light from very high aspect ratio scintillators, right? So, these pixels are quite small, but you need to make the detector actually quite long to make it efficient, right? You simply need a lot of volume, otherwise you're not going to intercept much of the radiation, right? So the question is, if I produce some light, somewhere here, right, how efficiently does that light travel to the side? Where does it go, right? Does it stay confined in this type of system, or does it leak out, right? So what happens next? And furthermore, right, how can I figure out where this event is, right? I'm making measurements on two sides over here. I don't make measurements in the middle, right? So how do I know where along this rod has the event taken place, right? So that's my next problem that I'm trying to solve, okay? Okay, so, and in order to do that, we can talk a little bit about the light collection in this kind of high aspect ratio scintillators. So we can think about what happens in radiation interaction, right? So let's say that there is a gamma ray. It can be neutron, but let's say that it's a gamma ray. It produces, some interaction here. There's an electron which is produced. Let's see here. Electron which is produced, and that electron undergoes wiggly path. It escapes and deposits some fraction of its energy inside of this rod. Okay, this is my electron. Okay, so what that does now, it produces a flash of light. So there's some energy deposition, and there's a flash of light, which we call scintillation, and it's isotropic, right? So I have light which is emitted in all directions. Okay. So now the question is, right, what happens to that light? And you can imagine now, I could maybe do something like I could make a perfect mirror, here, such that all of this light would just kind of bounce back and forth all the way to the end, right, off of this mirror, and get all the way to one side, and everything that goes this way, right, would end up on the other side. And then I would put my photosensor here. I'm going to call it just PS photosensor on one side, photosensor on the other side, and I'm going to somehow collect everything, right? But it turns out that, you know, mirrors are not as reflective as you might think, actually. So, you know, mirrors maybe will have at best maybe something like 97% reflectivity. And so the problem is, you know, really the number of bounces is so large that you will lose the light. And also it's just very inconvenient if you had to put mirror on the side of these, on the side of the stimulator. So there are a couple of other things you can do, okay? One of the things you can do is you can wrap the scintillator with some material which produces kind of like a diffuse reflection. So forget about using something that is called specular reflection, which is what mirror does. Specular reflection means, you know, you incident on a mirror and you bounce off at one direction such that the incident angle is equal, you know, to the outgoing angle. Alpha equals beta, basically. That's your specular reflection. This is your mirror. Instead, let's just think about the diffuse reflection. And on the diffuse reflector, what happens is your incident at some angle and you scatter off in all directions, okay? With, you know, some probability of angle, which is usually a cosine described by a cosine function, something called a Lambertian reflector. And so that's something you can do with materials such as Teflon. For example, you could wrap your simulator with Teflon and then just rely on these diffuse reflections to collect as much as possible of the light on two sides. And then there's a third thing, which is something really neat that the nature does, which you can do, which is called total internal reflection. Or TIR. And the total internal reflection, what it does essentially is, you know, you can imagine that I have a light which is incident onto a boundary, right? And which is highly polished, so it's smooth, okay? And then I have some normal to that boundary. So if I have a light which is incident at some angle, you know, at some critical angle, that light will actually reflect with, you know, 100% efficiency. This is called total internal reflection. And all the rays which would fall sort of in this region over here, so any angle, you know, that would be incident angle which would be greater than that total internal reflection angle would also get reflected. But the rays which would be incident at smaller angles, we're measuring angle from the normal, so this would be smaller angle, would actually just leak out. Okay, so I actually didn't draw this right. It would refract in such a way that it would emerge out of your simulator and it would escape. Right? So I can just resort to this idea where I'm going to just capture everything that is all the simulation which is emitted at a particular angle, right, and lose everything else, right? That will be my that will be one idea how I can do this without doing anything special, right? I just need a smooth surface, and I collect only a fraction of the light, but that light now can get reflected. So I lose a lot of light in the beginning, right, because a large fraction of it is lost. However, the rest of the light that is captured actually propagates very efficiently, you know, through this by this total internal reflection process, which is essentially lossless. You know, the only way how you can lose light really in this process is going to be by scattering, right? So the surfaces are not perfectly smooth, so maybe light can encounter a little bit of inhomogeneity, a little bit of roughness on the surface. It can scatter, and that's how you can lose light. Otherwise, light could propagate, you know, basically indefinitely. Now, of course, there's something else I didn't talk about, which is that simulators also absorb light, right? So over long distances, and you know, any light, you know, that propagates, you know, through a system will get absorbed, you know, and the rate of that absorption, right, depends on the distance that light travels. So you can imagine that light that is produced on one side travels to the other side will, you know, once it makes it to the other side, will be significantly weaker right? So that's the whole idea, how you can actually detect the position at which this light is created in the simulator. You can look at the ratio that you get, from photosensor. Let's call this photosensor 1, and this is a photosensor 2. So you can look at the ratio between the signal I get, the photosensor 1 to photosensor 2, and use that in order to infer the position, right? Simply because, so if I get the same amount of light, then I infer that that light was produced somewhere in the middle, right? If I get more light on the side 1, that the event happened closer to photosensor 1, and vice versa, right? If I get more signal on photosensor 2, I get I learned that I have produced my event closer to photosensor 2, right? So that would be my that would be the approach. And in practice, how you can measure that, how you can characterize this, and this is real experimental data from that detector that you have seen. So this is that central module that I talked about. So you have array of plastic scintillators here, instrumented with silicon photomultipliers on 2 sides. You use a gamma ray source, which you collimate, which means you put this LED around it such that the gamma rays can travel only one direction, right? So they can only go in this direction. So now imagine I can just move this assembly back and forth, and I can measure how much signal I get on one side and how much I get on the other side, right? And when I do that, I can measure that on 2 sides, and I get this kind of plot, which is shown on the bottom over here, right? So this is basically the experimental measurements, and you can see based on the source position, I get a different amount of charge on 2 sides, right? So I can now calibrate the position based on the known amount of signal that I get on the 2 sides of this kind of assembly. And I can actually quite well simulate this as well, right? So I can simulate, of course, I can simulate radiation interaction with these plastics. I can simulate production of light. And the next step is I need to simulate the transport of light through these systems, through the plastic scintillators. And to do that, I have to take into account various processes like absorption, scattering, total internal reflection, etc. Right, all of these things. Okay, and so to do that, there are different tools available, but the one we like to use is called Jan4. It's an open source code that anybody on this call can actually retrieve. Yeah, there's there was a question. So Jan4 light transport is very powerful. This is open source code developed at CERN, at the Center for European Nuclear Research, and anybody can actually use this. And these are examples of various types of processes that can be simulated in Jan4 that you can use. So we've been able to simulate this quite well, taking into account various processes that occur in the light transport. Is there a freeze? I'm not sure about the freeze. I hope you can hear me. No? Okay, maybe it's on the
Yeah, I can hear you fine, okay. Igor.
Okay. All right. One other topic. Okay, so this is interesting, I think. Always a question of uniformity. Right. So how uniform is light collected, from a scintillator? Let's just assume that I have a scintillator, which is this cylinder over here. Okay, this represents a scintillator, and then I have some kind of photosensor on the bottom. Let's just say that I have my. Let's just not worry about what that is, but I have a photosensor over here. Imagine. And now imagine that I have my radiation incident at 2 different positions. And let's not worry about the vertical axis here. Let's just look at the horizontal one. Let's say that one event takes place on this side, okay? And then I have another event that takes place over here. Okay. So now I get scintillation. Change the color here. You get scintillation light emitted in all directions. And that scintillation light bounces, over, and some of it makes it down onto this photosensor on the bottom, right? So it illuminates this photosensor. And the point is, so if I have this event on the left, what I will find out is when I actually simulate this light transport, I will see that one side of my photosensor will light up a little bit brighter than the other side. The side on which the event happens is typically going to be the one that will get illuminated stronger than the other side, right? So then on the other side, I would have the opposite thing happen, right? So right, I would have the events happen on the other side. And you might say, well, so why would I need to worry about that? What's the big deal about that? And the point is that even in detectors that are not really nominally position sensitive, such as these photomultiplier tubes that I talked about, that there are slight non-uniformities in the photocathode that is the element of the photomultiplier tube that converts light into photoelectrons. And the reason that is because this photocathode is very thin, right? So when you have something very thin, you cannot make it perfectly flat, just like I cannot draw it perfectly two straight lines. There will be differences in the thickness as a function of position, right? And as a result of that, there will be different quantum efficiencies. I will say, for example, lower quantum efficiency maybe here where it's a little bit thinner, and higher quantum efficiency over here. Okay? Maybe high quantum efficiency here, low over here. Okay? So now, depending then how the light illuminates this photosensor will depend how many photoelectrons I see. So I may interpret that as more maybe radiation, higher energy radiation interacting with my detector if I see more photoelectrons produced, but that could be simply because my radiation interaction took place in such way that the part of the photosensor that got illuminated by light is slightly more efficient. Right? So this is quite a bit of a problem if I want to, for example, use these detectors to measure energy in a very reproducible way, right? Because depending on where the event happens in the detector, I will measure a slightly different result every time, even if I have exactly the same energy deposition, the same amount of light emitted, I may be measuring slightly different signals simply because of this non-uniformity. So one way to deal with that is to scramble the light, okay? So don't allow the light to be non-uniformly distributed on the photosensor, but use something that could scramble that light. So regardless of where the light comes from, it can be scrambled such that this photosensor gets homogeneously illuminated, right? And one of the ways to do that is would be to use something like the light guide, okay? So you can imagine that at the end of this simulator, I could use like a cone of light, such that light that is incident from my simulator can bounce many times, and regardless of where it enters, it will be homogenized, right? And it arrives at the smaller detector, at the smaller photosensor, and regardless of where it comes from, it will produce a more or less homogeneous distribution of my photosensor. So I can have a very reproducible illumination. That's kind of one of the ideas how you can do, like how you can improve this uniformity and why it's important. All right, so let's see if I have other questions. Okay, great. All right, so I want to talk one more other thing, which is wavelength shifting. This is really interesting. This is a picture from Professor Glenn Knoll's book, which is, some of you may already, I think you've probably heard about it by taking some of the earlier lectures by one of our very famous former faculty members in radiation detection and measurement. And he has this nice picture here and shows, in his book, that shows how light can be collected using the concept of wavelength shifting. So in this particular idea, what happens is I have simulators, which are these blocks over here. And then what I have along the simulators is I have a light collector, which is like a little pipe, a tube, which is loaded with something that is called a wavelength shifter. So how does this work? You can imagine now simulation, which is kind of trapped inside of this simulator, and it's basically bouncing around. Light is bouncing around, and occasionally it traverses this wavelength shifter. Okay, And when it gets traverses this wavelength shift, a fraction of that light will get absorbed. It will get re-emitted. Okay, and I will draw that with a different color because it gets re-emitted at a longer wavelength. This is why it's called the wavelength shifter. So I'll draw that as the red light. And when it gets emitted like that, it gets emitted again in all directions, and fraction of that light will get trapped and will propagate down this rod, right? And now it will emerge and be collected on two sides. Okay, so this can be quite useful for two different reasons. One is because it allows light to basically be funneled, in one direction. The other one is that sometimes it's beneficial to shift the light to longer wavelengths, which can be detected with a little bit higher efficiency in some cases. Okay. So I did want to highlight one new idea of how this can be used. And this is called, this is a very new idea in the literature. This is described in this paper that you can access on arXiv. And this is called liquido. And what is liquido? Liquido is essentially an opaque scintillator, a scintillator that has a lot of scattering, but very little absorption. And the idea is that one can introduce a lot of optical fibers into this type of scintillator. You can think of a very highly scattering medium, a little bit like a cloud or milk, right? And imagine that, and light has a lot of trouble getting out of that kind of medium. It scatters a lot. But what you do is you can introduce a lot of these wavelength shifting fibers into the medium and then rely on that scattering to ultimately cross one of these optical fibers, shift the light, right, in such a way that it can be then trapped in this wavelength shifting fiber and emerge on the two sides, right? And this is quite interesting now because you can reconstruct the positions, of radiation events that occur anywhere in this opaque scintillator, even with the scintillator being opaque. We usually think of the scintillator as needing, that needs to be very transparent as possible, so the light can propagate over a long distance. And here we play this trick in which we basically introduce a lot of these fibers and capture the light where it's produced, right? Instead of requiring the light to travel far away. And this is very powerful. People think that this is actually going to enable some of the next generation measurements for detection of neutrinos, maybe above ground, because one can very exquisitely measure what happens in the medium over large volumes of the medium. And these images show some of the simulations that show the types of events that can be measured and reconstructed and interpreted very well. And that brings me to only half of what I wanted to say in 1 hour today. But I think we'll stop here. Maybe I'll take any additional questions on this.
Hey, Igor, this is really great. I think we just have to invite you back to give the other half, of the presentation that you prepared.
Yeah.
So questions, any questions from the students?
We already had a lot of questions, which was terrific. I really liked the discussion so far.
I know we already had questions during the talk.
Yeah, so I stopped talking now, no talk. Yeah. But anyway, so I think with this last idea, I just wanted to motivate you to think this is really thinking outside of the box, opaque scintillators, like what would you do with that, right? And this is an entirely new idea. It hasn't quite been people actually starting to experimentally demonstrate that. There are quite a few attempts, and if it works, it will be very transformational idea for many measurements. But I hope you got a taste, a little bit of I think, various things you want to think about and worry about. The devil is in the details with these measurements. Question is, how about the collection time? This is a fantastic question. Thank you for asking for that. One of the really cool things about this idea of the high scattering medium is that it almost works like a time stretch device. Okay, this is what simulations show. We'll see what the experiments will do. But essentially, because the light takes this very, very complex, tortuous path, through the medium, it takes much longer for the light to actually reach the destination. Okay, so people predict based on simulations, but with realistic parameters for scattering, that you can expect that the collection time will be typically an order of magnitude longer than in a traditional simulator. So imagine that you have all these events developing at a speed which is about 10 times slower than you would normally get. So it's almost like you slow down the light by a factor of 10. Okay? Great question. Composition of the material. So there are a couple of things that are being discussed right now. And so basically we need a lot of scattering. And one of the ways, we're looking into that, one of the materials which I didn't have time to talk about today is called water-based scintillator, which is basically dispersing little particles, basically a scintillator into water. And whenever you have some kind of inhomogeneity, you have some kind of interface, you can get scattering on that interface. So the idea is to have a lot of that scattering. So there are different ways how you can do that. Some kind of emulsion is typically what you're looking at, and then you worry about that emulsion remaining stable, right? Because you don't want it to sort of separate, right? So you want some kind of emulsion, and then furthermore, you don't want that material to absorb. You just want it to scatter, right? So your path of the light is actually quite long, because light undergoes a lot of scattering, right? But you don't want it to be absorbed until it gets to the fiber. That's where you want it to be absorbed.
Great.
Mm-hmm.
Well, Professor Jovanovic, thank you again for this very nice presentation. We really appreciate you taking the time to talk to us about scintillators and light collection and photodetectors. This has been really great. So thank you. And we will see everyone at the next.
Mm-hmm.
Bye. Thanks.
Thank you. Thanks, everyone.